x86. x86 is the architecture most gamers have trusted for years, even if they've never once thought about what's actually inside their laptop. If you've owned a gaming laptop, chances are it ran on a processor from Intel or AMD. That's x86. The loud, power-hungry, performance-obsessed backbone of PC gaming. The roots of x86 go all the way back to the late 70s. Intel's 8086 chip launched on June 8, 1978. The single processor started as architecture that now powers over 90% of the world's PCs and laptops. But don't let that age fool you. It's been upgraded more times than your GPU drivers. It's built on a complex instruction set, or CISC, meaning it can execute chunky, complicated commands directly in hardware. In normal human terms, it brute forces tasks like it's allergic to losing. Gaming laptops love x86 because of high clock speeds and strong single-core performance. Most games still care about one core doing heroic amounts of work, and x86 delivers. That's why your laptop sounds like it's preparing for takeoff when you launch a AAA title. Performance first, eardrums later. Another huge win? Compatibility. Windows is built around x86. Nearly every PC game is optimized for it. Anti-cheat systems, mod tools, random decade-old software you refuse to uninstall. It all just works. I personally think this is the most underrated advantage of x86. You don't realize how much you depend on compatibility until you try running a 15-year-old game on a different architecture and it just doesn't work. The downside? Efficiency. x86 chips can drink power like it's a free refill and produce heat that turns your keyboard into a mild hand warmer. Still, when it comes to gaming laptops, x86 isn't subtle. It's fast, loud, and built to win. ARM. ARM is the quiet genius of the CPU world. No fans spinning like helicopters. No dramatic overheating. Just calm, efficient performance while your battery percentage barely moves. If you've ever used an iPhone, you've been running on ARM. Apple's A-series chips are built on this architecture, and they're obsessed with efficiency. Unlike x86's complex instruction set, ARM uses RISC, a simpler, cleaner set of instructions. In human terms, fewer steps, less wasted energy, more done per watt. The result? Your phone feels ridiculously fast while sipping power like it's on a diet. You can game, stream, doom scroll for hours, and still end the day with 30% battery left. Try that on a gaming laptop and you'll be hunting for an outlet before lunch. ARM started back in the 1980s in the UK, specifically 1985. Acorn Computers built the first ARM chip in Cambridge, originally called the Acorn RISC machine. It was designed for a desktop computer almost nobody remembers, but the architecture ended up inside over 250 billion chips worldwide. That's not a typo, billion, with a B. No one expected it to take over billions of smartphones, but efficiency scales beautifully. As apps got heavier and cameras started shooting cinema-quality video, ARM chips evolved. More codes, powerful GPUs, dedicated AI engines. Now they're not just efficient, they're fast enough to embarrass some laptops. The biggest flex? Performance per watt. That's why your iPhone doesn't need a fan. It doesn't roar, rattle, or beg for a cooling pad. It just gets slightly warm and keeps going like nothing happened. ARM doesn't try to dominate loudly. It just quietly runs the modern world. One 12-hour screen time session at a time. Apple Silicon. Apple Silicon is the moment laptops stopped sounding stressed all the time. When Apple introduced the M1 chip in 2020 and moved away from Intel processors, it wasn't just a routine upgrade. It was a full architectural shift. MacBook Pros went from traditional x86 chips to Apple's custom ARM-based silicon, designed entirely in-house. At its core, Apple Silicon uses the ARM instruction set, built around efficiency. But this isn't a phone chip stretched to fit a laptop. It's a full system-on-a-chip design. CPU cores, GPU cores, unified memory, neural engine, media encoders, all on one tightly integrated package. Everything communicates faster because it's physically closer together. Less waiting, less wasted power. The result is performance that feels almost suspiciously smooth. You can edit 4K video, export massive projects, compile code, and run heavy creative apps without the laptop turning into a space heater. Battery life jumped dramatically, and the fans often stay quiet enough to make you wonder if they're even installed. I'll be honest, the first time I used an M1 MacBook, I forgot to charge it, and it still lasted the entire day. I genuinely thought the battery indicator was broken. Unified memory is another big shift. Instead of separate RAM and VRAM pools, everything shares the same fast memory. That reduces bottlenecks and keeps creative workflows fluid, especially in video editing and 3D work. There were early compatibility hurdles, but translation software handled most of it quietly. Apple Silicon didn't just make MacBooks faster. It made them efficient in a way that feels almost unfair to the competition. RISC-V. RISC-V is the rebel of the CPU world. While x86 and ARM are tightly controlled ecosystems, RISC-V is open source. Anyone can use it. Anyone can modify it. No licensing fees, no corporate gatekeeping, just a clean instruction set and a build whatever you want attitude. Boards like those from Pine 64 helped bring RISC-V out of research labs and into the hands of developers and hobbyists. These aren't gaming monsters or flagship laptops. They're experimental playgrounds. Tiny boards running Linux, testing new ideas, proving that CPUs don't have to be controlled by a handful of tech giants. Like ARM, RISC-V follows a reduced instruction set philosophy. Simple instructions, efficient execution. But here's the twist. It's modular. You can start with a tiny base instruction set and add extensions for floating point math, security, AI acceleration, or whatever your project needs. It's like Lego for processor design. Performance today? It's improving fast, but it's not competing with high-end x86 or Apple Silicon chips yet. RISC-V boards are more about flexibility and learning than raw power. You don't buy one to run AAA games. You buy one to experiment, build, and maybe break a few things along the way. The real power of RISC-V isn't speed, it's freedom. Governments, startups, and researchers love it because it reduces dependence on proprietary architectures. GPU. The GPU inside a console is where raw graphics ambition lives. In the PlayStation 5, the graphics processor isn't just an add-on. It's the main character. While the CPU handles logic, AI, and background systems, the GPU is responsible for the thing you actually care about, what's on the screen. The PS5 uses a custom GPU built on AMD's RDNA 2 architecture. It's designed specifically for gaming workloads. High-resolution textures, complex lighting, ray tracing, massive open worlds, and stable frame rates. Unlike a PC where parts are mixed and matched, this GPU is tightly integrated with the console's memory and storage system. Everything is optimized to work together. That optimization is the secret sauce. Developers know exactly what hardware they're targeting. No guessing about configurations. No worrying about whether someone is running low VRAM. That's why games on consoles often look shockingly good for the hardware they're running on. The PS5 GPU supports hardware-accelerated ray tracing, allowing more realistic reflections and lighting. It pushes 4K resolution, high frame rates, and fast loading thanks to its unified memory and ultra-fast SSD pipeline. Of course, it's not upgradable. You can't swap it out when something better launches next year. What you buy is what you ride for the generation. But that's the beauty of it. Quick question. Which of these architectures is actually inside your main device right now? Drop it in the comments. And if you're finally starting to see how all these chips connect, hit the like button. It genuinely helps the channel. Quantum. Quantum computing is the hold my coffee level of processing. Google's Willow chip is a perfect example. Not something you'll find in a laptop or phone, but a glimpse at the future of computation. Unveiled in December 2024, the Willow chip packs 105 superconducting qubits. In a benchmark test, it completed a calculation in under 5 minutes that would take the world's fastest classical supercomputer an estimated 10 septillion years. That number is so big it makes the age of the universe look like a rounding error. Unlike classical CPUs or GPUs, it doesn't process bits as zeros or ones. It works with qubits, which can exist in multiple states at once. In human terms, it's like doing all possible calculations at the same time instead of one by one. Magic? Almost. Physics? Definitely. The Willow chip is part of Google's quantum research push, designed to run experiments in quantum supremacy, optimization, and simulation of complex systems like molecules or materials. It's not about gaming or spreadsheets. It's about solving problems that would take classical supercomputers millions of years. Quantum chips are extremely delicate. They need near absolute zero temperatures and insanely precise control. One stray vibration or electromagnetic hiccup, and the calculation collapses. In other words, don't expect to toss a Willow chip in your backpack anytime soon. But when it works, the results are mind-bending. Optimization, cryptography, drug discovery, AI simulations, Willow can explore solutions far beyond what traditional computers can handle. It's slow, fragile, and weird compared to what you're used to, but that's the point. AI, NPU. The NVIDIA H100 is where raw computing meets futuristic intelligence. Unlike CPUs or GPUs that handle general tasks or gaming, the H100 is a neural processing powerhouse, an AI accelerator built specifically for machine learning, deep learning, and massive data crunching. It's designed to accelerate neural networks, making training and inference faster than you thought physically possible. Built on NVIDIA's Hopper architecture, the H100 packs 16,896 CUDA cores and 528 fourth-generation Tensor cores. It can hit nearly 4,000 teraflops in FP8 precision. For context, that's more raw AI compute than entire data centers had just a decade ago. It doesn't just process numbers. It predicts, optimizes, and crunches massive datasets in parallel. Think of it as a GPU on steroids with a PhD in AI. Data centers and research labs love it. Large language models, image recognition, recommendation systems, autonomous vehicle training, all of that gets a huge performance boost. What might take days on a standard GPU cluster can happen in hours or minutes on H100 hardware. Of course, it's not for casual use. You won't drop one on your desktop to run Minecraft faster. It's expensive, draws around 700 watts under full load, and is designed for data center scale, not your desk. But for organizations building the next generation of AI, it's basically a jet engine strapped to a calculator. The H100 isn't just processing power, it's intelligence acceleration. It takes tasks that humans could never do manually and completes them at mind-bending speed. In the AI world, this chip is the difference between experimental and game-changing. MIPS. MIPS is the architecture that powered one of the most iconic consoles of the 90s. The Nintendo 64 ran on a MIPS-based CPU, specifically a 64-bit NEC VR4300 running at 93.75 MHz. That sounds laughable today, but in 1996, it was enough to render real-time 3D worlds that completely redefined what people expected from a home console. MIPS uses a reduced instruction set, or RISC, which makes it simpler and faster at processing instructions per cycle, perfect for a console that needed to push 3D graphics without breaking the bank. With MIPS, the N64 could handle real-time 3D worlds, complex camera movements, and physics calculations that blew minds in 1996. Games like Super Mario 64, The Legend of Zelda: Ocarina of Time, and GoldenEye 007 weren't just fun. They were revolutionary, showing what a console could do in 3D when the hardware was tuned correctly. I spent an embarrassing amount of hours playing GoldenEye split screen with friends, and at the time, none of us had any idea that a MIPS chip was making it all possible. We just knew it looked incredible. The architecture's simplicity made development predictable and efficient. Developers could squeeze out performance, optimize memory usage, and take full advantage of Nintendo 64's graphics pipeline. That's part of why those games still hold up today in terms of gameplay and innovation. Of course, there were limits. The N64 had relatively little RAM, and its graphics hardware couldn't match the raw polygon counts of later consoles. Textures were blurry, draw distances were short, and anti-aliasing was basically a fantasy. But MIPS didn't just run the N64. It made 3D gaming approachable, fast, and fun, at a time when most consoles were still figuring out polygons. It's a reminder that sometimes smart architecture beats raw horsepower. PowerPC. PowerPC is the architecture that gave the Nintendo GameCube its quirky charm and surprisingly powerful performance for its size. Released in 2001, the GameCube used a custom IBM PowerPC CPU. Unlike the similar RISC chips in earlier consoles, PowerPC was designed for balanced performance, strong enough to handle 3D graphics, physics, and AI, but efficient enough to fit inside Nintendo's famously compact, cube-shaped console. It was a masterclass in engineering trade-offs. Small, quiet, and capable. The CPU's architecture allowed developers to get creative with memory and graphics pipelines. Games like Super Smash Bros., Melee, Metroid Prime, and The Legend of Zelda pushed vibrant 3D worlds and smooth frame rates that surprised everyone, considering the tiny disk-based system. PowerPC made optimization easier and predictable, letting developers squeeze the most out of the hardware. Downsides? The GameCube's architecture wasn't as straightforward as x86 or standard ARM designs. It required specialized knowledge, and porting games from other systems could be tricky. And while the CPU was fast, the console's memory bandwidth and storage medium, mini disks, still limited maximum texture quality and load times. But PowerPC wasn't about generic. It was about giving Nintendo a unique platform that ran quiet, ran cool, and let its developers craft some of the most beloved games of that generation. FPGA. FPGAs are the Swiss Army knives of the chip world, and Tesla helped put them on the map in a very futuristic way. Unlike fixed CPUs or GPUs, FPGAs, short for Field Programmable Gate Arrays, are reconfigurable hardware. They can be programmed to perform specific tasks extremely efficiently, and then reprogrammed later if the requirements change. Tesla actually used FPGAs in its early autopilot hardware around 2014 to 2016, back when the self-driving system was still being prototyped. FPGAs handled sensor fusion and real-time data processing from cameras and radar during those early experimental stages. Eventually, Tesla moved to custom ASICs for production vehicles because they're more power efficient at scale. But FPGAs were the flexible foundation that helped get the system off the ground. And outside Tesla, FPGAs are still widely used across automotive, aerospace, defense, telecom, and industrial systems wherever reconfigurable low-latency hardware is needed. The beauty of FPGAs is flexibility. You can update the chip's behavior, refining features, or improving functions without physically replacing the hardware. It's like giving your system a brain that keeps learning and evolving after deployment. Performance-wise, FPGAs can process huge streams of data in parallel, which is perfect for real-time systems where milliseconds matter. They handle vision, radar, and sensor inputs simultaneously, crunching numbers faster than a human brain can react. The trade-off? FPGAs aren't as power efficient as specialized ASICs for high-volume tasks, and programming them is tricky. Designing a custom architecture that balances performance, energy use, and cost requires serious engineering. Still, in the automotive and industrial world, FPGAs are quietly revolutionary. And that's every CPU architecture from x86 gaming laptops to quantum chips that make classical supercomputers look like calculators. Each one solves a completely different problem: raw performance, efficiency, flexibility, or just straight-up futuristic intelligence. Which architecture surprised you most? Drop it in the comments. I'm genuinely curious. If this finally made CPU architecture make sense, subscribe so you don't miss the next one. Now, here's the thing. You just learned what architectures power your devices. But one of those devices, your GPU, has its own confusing spec that trips up almost everyone: VRAM. 128 megabytes, 512 megabytes, 2 gigabytes, 4 gigabytes, 8 gigabytes, 16 gigabytes, 24 gigabytes. Those numbers are plastered on every graphics card, but most people have no idea how much they actually need. Why did old GPUs ship with just 128 megabytes and somehow run games fine? Why do modern cards need 24 gigabytes? And is doubling your VRAM even worth the price? Or is it just an expensive safety blanket? That's exactly what we're covering next. Every VRAM size explained simply, what each tier actually handles, which one matches how you game or create, and where the real sweet spot is without overpaying. Click the video on screen right now, and I'll see you there.